So here's something to think about as you settle in tonight. Everything around you, and I mean everything, the pillow under your head, the air filling your lungs right now, the glass of water on your nightstand if you've got one there, all of it is made from the same basic set of ingredients. About 90 or so elements that occur naturally, and that's it. That's the whole pantry. The entire universe, every star, every rock, every living thing, every ocean. It's all assembled from this surprisingly short list. And for most of human history, nobody knew that. Nobody even suspected it. People looked at the world and saw infinite variety, endless complexity, and they had no idea that underneath all of it was a simple, elegant structure, just waiting to be uncovered. The story of how we figured that out, how we went from total confusion about what stuff is made of to this beautiful, organized chart that hangs on the wall of every chemistry classroom in the world. That story is one of the greatest detective tales in all of science. It spans centuries. It involves alchemists and revolutionaries, loners and rivals, people who were laughed at and later proven right, people who were celebrated and later proven wrong. And the really wonderful thing is that the periodic table isn't just a list. It's a map. It's a map of reality itself. And the fact that it works, that it predicts things nobody has even discovered yet, that's one of the most astonishing achievements of the human mind. But we're getting ahead of ourselves. Let's go back. Way, way back. The ancient Greeks are a good place to start because they were the first people we know of who really sat down and asked the question in a serious, philosophical way. What is stuff made of? What's the most basic ingredient? Now, they didn't have laboratories. They didn't have microscopes or spectrometers or anything like that. What they had was logic, and they had arguments, and honestly, they had a lot of time to sit around and think. And the answers they came up with are fascinating, not because they were right, but because of what they reveal about how hard this question really is. Around 450 BC or so, a philosopher named Empedocles proposed that everything in the world was made from 4 fundamental roots, which later thinkers would call elements: earth, water, air, and fire. That was it. Every substance you could see or touch was just some combination of those 4, mixed in different proportions. Wood was mostly earth and fire. Steam was water and air. A rock was almost pure earth. It's a beautifully simple idea, and if you think about it, it's not a terrible first guess. You can see how someone watching a log burn might conclude that the fire was being released from within the wood, while the ash left behind was the earth component, and the smoke drifting upward was the air escaping. It makes intuitive sense, even if it's completely wrong. Aristotle picked this up and ran with it, adding his own refinements. He suggested that these 4 elements could transform into one another through changes in their fundamental qualities: hot and cold, wet and dry. Water was cold and wet. Fire was hot and dry. Change the qualities, and you change the element. This idea, that one substance could be fundamentally transformed into another, would echo through the centuries in ways Aristotle probably never imagined. Because if you believe that elements can transform, well, then maybe you can turn lead into gold. And that belief launched a 1,000-year quest that we call alchemy. But before we get to the alchemists, there's another Greek thinker who deserves a moment here, because he came remarkably, almost eerily close to the truth. His name was Democritus, and he lived around the same time as Empedocles, maybe a little later. Democritus proposed something radical. He said that if you took any piece of matter and kept cutting it in half, and then in half again, and again, and again, Eventually, you'd reach a piece so small it couldn't be cut anymore. He called these smallest pieces atomos, which literally means uncuttable, atoms. And he believed that everything in the world was made of these atoms, moving through empty space, combining in different arrangements to create all the variety we see around us. Think about that for a second. 2,400 years ago, this man sitting in a Greek coastal town essentially described the atomic theory of matter. Not perfectly, not in detail, but the core insight that matter is made of tiny, indivisible particles whose arrangement determines the properties of the substance. That's basically right. It's extraordinary. But here's the thing. Democritus couldn't prove it. He had no way to test it, no experiments to run. It was pure reasoning, pure intuition. And because Aristotle's system was more elaborate, more connected to observable experience, and because Aristotle was, well, Aristotle, the most influential philosopher in the Western world, it was the four-element theory that won out. Democritus's atoms were largely forgotten for 2,000 years. 2,000 years. Imagine being that right, that early, and having nobody listen. So the four-element model dominated Western thinking about matter for an incredibly long time. And layered on top of it came alchemy, which flourished first in the Islamic world during what's sometimes called the Islamic Golden Age, roughly the 8th through the 14th centuries. Now, alchemy gets a bad reputation. People think of it as this mystical, fraudulent pursuit. Old men in robes trying to turn lead into gold while muttering incantations. And sure, there was some of that. But the best alchemists were serious, meticulous experimenters who developed techniques and discovered substances that would form the foundation of modern chemistry. Take Jabir ibn Hayyan, who worked in the 8th century, probably in what's now Iraq. Some historians debate exactly which works attributed to him he actually wrote, since a whole tradition of texts accumulated under his name over the centuries. But the body of work associated with Jabir is remarkable. It describes distillation, crystallization, the preparation of acids, including what we'd now recognize as hydrochloric acid and nitric acid. These are real chemical achievements. Jabir also refined the theoretical framework, proposing that metals were composed of two fundamental principles, sulfur and mercury, in different proportions and purities. Change the proportions, purify the ingredients, and you could, in theory, transmute one metal into another. It was wrong, but it was a productive kind of wrong. It drove people to experiment, to heat things and dissolve things and combine things and carefully observe what happened. And that's really the key contribution of alchemy to our story. Not the gold making, which never worked, but the experimental culture. Alchemists built furnaces. They invented laboratory glassware. They learned to work with dangerous substances carefully, or sometimes not carefully enough. They kept records, sometimes in code, of what they tried and what happened. They were, in a very real sense, the first chemists, even if they wouldn't have used that word. As alchemy migrated into medieval Europe, it picked up new practitioners and new ideas. The Swiss physician Paracelsus, working in the early 1500s, shook things up considerably. His real name was Theophrastus von Hohenheim, but he gave himself the name Paracelsus, probably meaning beyond Celsus, a reference to a famous Roman medical writer. Paracelsus was, by all accounts, an incredibly difficult person. Arrogant, combative. He once publicly burned the books of the ancient medical authorities to show his contempt for received wisdom. He was fired from academic positions. He wandered across Europe. He made enemies everywhere he went. But he also had genuinely important ideas. Paracelsus argued that the goal of alchemy shouldn't be making gold. It should be making medicine. He introduced the idea that diseases had specific chemical causes and could be treated with specific chemical remedies, which was revolutionary at a time when medicine was still largely based on the ancient theory of balancing the four humors. And he expanded the alchemical theory of matter, proposing 3 fundamental principles instead of 2: sulfur, mercury, and salt. Different substances contained these 3 principles in different combinations. It still wasn't right, but it was another step, another nudge toward the idea that matter has a limited number of fundamental components. Here's what I find so interesting about this whole period. For centuries, really smart people were circling around the right answer without quite reaching it. They knew intuitively that the bewildering variety of the material world must arise from a smaller set of building blocks. They just couldn't figure out what those building blocks actually were because they didn't yet have the tools or the conceptual framework to isolate individual elements and prove that they couldn't be broken down further. They were trying to solve a puzzle in the dark, feeling the edges of pieces they couldn't see. The breakthrough, when it finally came, arrived in the late 1600s and early 1700s, and it came from a shift in thinking that seems obvious in hindsight, but was genuinely radical at the time. Instead of starting from philosophical principles and reasoning downward toward the nature of matter, a new generation of thinkers started from experiments and reasoned upward. "Show me," they said. "Prove it. If you claim something is an element, demonstrate that it can't be broken into simpler substances. If you claim 2 things are different, show me how their behavior differs." This is the birth of chemistry as we know it, and the person who usually gets credit for crystallizing this new approach is an Anglo-Irish gentleman named Robert Boyle. Boyle published a book in 1661 called The Skeptical Chymist, and the title tells you a lot about his attitude. He was skeptical. Skeptical of the 4 elements, skeptical of the 3 principles, skeptical of anything that couldn't be demonstrated through careful experiment. Boyle proposed a definition of an element that was, for its time, beautifully practical. An element, he said, was a substance that couldn't be broken down into anything simpler by any known chemical means. That's it. No philosophical baggage, no mystical properties, just a straightforward operational definition. Can you decompose this substance into something else? No? Then it's an element. Yes? Then it's not. Now, Boyle himself didn't identify a whole list of elements. That would take another century of painstaking work. But he gave the world the right question to ask, and that mattered enormously. He also did important experimental work on the behavior of gases, and you might remember Boyle's law from school, the one about pressure and volume being inversely proportional. Same person. He was a remarkably careful experimenter, and he helped establish the idea that chemistry should be a quantitative science, a science of measurement, not just qualitative observation. The decades after Boyle saw a slow accumulation of knowledge. New substances were isolated. Phosphorus was discovered around 1669 by a German alchemist named Hennig Brand, and the story of that discovery is honestly one of the strangest in all of science. Brand was convinced that the secret to the philosopher's stone, the legendary substance that could transmute base metals into gold, might be found in human urine. Yes, really. The golden color, he thought, might be a clue. So he collected enormous quantities of urine, reportedly around 1,500 gallons of the stuff, and he boiled it down and heated the residue and distilled it. And after a long and presumably extremely unpleasant process, he ended up with a waxy white substance that glowed in the dark. He'd discovered phosphorus, element number 15, and he'd done it by accident while trying to do something completely impossible. That's the history of science for you. Sometimes, the wrong question leads you to the right answer. By the mid-1700s, the list of known elements was growing, though nobody was calling them that yet in any systematic way. Cobalt, platinum, nickel, bismuth, zinc, these were being identified and characterized, mostly by metallurgists and pharmacists working with ores and minerals. But the theoretical understanding of what an element actually was at the deepest level was still muddled, still tangled up with an idea that would need to be demolished before chemistry could truly advance. That idea was phlogiston, and the man who demolished it would lose his head for it, quite literally. His name was Antoine Lavoisier, and he's often called the father of modern chemistry, and that title is well-deserved. Lavoisier was born in Paris in 1743 into a wealthy family. His father was a lawyer, and young Antoine studied law too, but his real passion was science. He had this incredible combination of qualities that you don't always find in one person. He was meticulous, he was imaginative, he had access to money for expensive equipment, and he had the intellectual courage to challenge ideas that everyone around him accepted as obvious truth. And the idea he challenged, phlogiston, had been the dominant theory in chemistry for nearly a century. So let's talk about phlogiston for a moment, because you need to understand what Lavoisier was up against. The theory was developed in the late 1600s by a German physician named Johann Joachim Becher, and later refined by Georg Ernst Stahl. The basic idea was this: when something burns, it releases a substance called phlogiston. Phlogiston was supposed to be this invisible, weightless, or sometimes even negatively weighted substance contained within combustible materials. When you burned a piece of wood, the phlogiston escaped into the air, and what was left behind, the ash, was the dephlogisticated material. When you heated a metal and it turned into a powdery residue, which we now call a metal oxide, the explanation was the same. The metal had lost its phlogiston. And here's the thing. The theory actually worked pretty well for a lot of observations. It explained why things burned. It explained why metals corroded. It even provided a framework for understanding why some reactions happened and others didn't. The problem was that it was completely wrong, and the clue was hiding in plain sight, on the scale. Because when you burned metals, when you heated them in air, and they formed that powdery calx, the calx weighed more than the original metal. Not less, more. If burning meant losing phlogiston, why would the product be heavier? That's like saying you took something out of a suitcase and the suitcase got heavier. It doesn't make sense. Some phlogiston supporters tried to rescue the theory by proposing that phlogiston had negative weight, that it was a substance with levity instead of gravity, which honestly should have been a red flag. When you have to invent a substance with impossible properties to save your theory is probably in trouble. But people clung to it because it was familiar, because it was taught in universities, because the alternative wasn't clear yet. Lavoisier changed all of that. He didn't do it with one dramatic experiment. He did it with years of careful, systematic work. His approach was deceptively simple, but revolutionary. He weighed everything. Before the reaction, after the reaction, the gases involved, the solids, the liquids, everything. He built sealed systems so nothing could escape unaccounted for. And in the early 1770s, he conducted a series of experiments that would overturn the entire framework of chemistry. One of his most famous experiments involved heating mercury in a sealed container with a known quantity of air. The mercury slowly formed a red powder on its surface, mercuric oxide, we'd call it now, and as it did, the volume of air in the container decreased. About 1/5 of the air was consumed. When Lavoisier then took that red powder and heated it even more strongly, it decomposed back into mercury and released a gas. That gas turned out to be exceptionally good at supporting combustion and respiration. A candle burned more brightly in it. A mouse placed in a jar of it could breathe longer than in ordinary air. Now, this gas had actually been isolated a few years earlier by Joseph Priestley in England and Carl Wilhelm Scheele in Sweden, working independently. Priestley called it dephlogisticated air, because in his framework, it was air that had been stripped of phlogiston and was therefore especially hungry to absorb more. Priestley actually visited Lavoisier in Paris in 1774 and told him about this discovery over dinner, and Lavoisier, to his credit, and also, some would say, to his discredit, because the question of proper attribution would become a sore point, Lavoisier took that information and ran with it. He recognized what Priestley hadn't fully grasped. This wasn't dephlogisticated air. This was a distinct substance, a component of the atmosphere, and it was the key to understanding combustion. Lavoisier named it oxygen from the Greek words meaning acid former, because he believed, incorrectly as it turned out, that oxygen was an essential component of all acids. That was one of his few significant errors. But the larger framework he built was extraordinary. Combustion wasn't the release of phlogiston. Combustion was the combination of a substance with oxygen. When a metal rusted, it wasn't losing phlogiston, it was gaining oxygen. That's why the calx weighed more than the metal. The metal had combined with something from the air. The weight gain was the weight of the oxygen that had joined with the metal. Suddenly, everything made sense. The books balanced. The numbers added up. And Lavoisier didn't stop there. In 1789, he published his masterwork, the Traité élémentaire de chimie, the elementary treatise on chemistry. And in that book, he did something that connects directly to the story we're following. He published a list of elements, 33 of them. Now, his list wasn't perfect. He included light and caloric, which is heat, as elements, and those aren't elements at all. But he also correctly identified oxygen, nitrogen, hydrogen, sulfur, phosphorus, carbon, and a host of metals as fundamental substances that couldn't be broken down further by chemical means. This was Boyle's definition, sharpened and applied systematically. Lavoisier was essentially saying, here are the building blocks, and here's how they combine, and we can track every gram of every substance through every reaction. He established the law of conservation of mass. That matter is neither created nor destroyed in a chemical reaction. The total weight of what you start with equals the total weight of what you end up with, always. Think about what that means. That single principle transformed chemistry from a collection of recipes and observations into a real science, a quantitative science, a science with rules you could count on. Every reaction became a kind of accounting problem, and if your books didn't balance, it meant you'd missed something, not that the rules had failed. But here's the part of Lavoisier's story that's hard to tell. The French Revolution came. Lavoisier was a brilliant scientist, but he was also a tax collector. He was a member of the Ferme Générale, a private company that collected taxes on behalf of the crown, and these tax collectors were despised by the French public, often for good reason. During the Reign of Terror in 1794, Lavoisier was arrested, tried, and convicted in a single day. The charges were essentially that he had added water to tobacco and had conspired against the people of France. The trial was a formality. He was guillotined on May 8, 1794, at the age of 50. The mathematician, Joseph Louis Lagrange, reportedly said the next day, "It took them only an instant to cut off that head, and 100 years may not produce another like it." And he was right. Lavoisier's death was one of the great tragedies of scientific history, a reminder that genius offers no protection from politics. But the work survived. The framework survived. And now chemistry had a clear mission: find the elements, characterize their properties, understand how they combine. The list that Lavoisier started with 33 entries was about to grow rapidly because the decades around the turn of the 19th century brought an explosion of new discoveries driven by a powerful new tool: electricity. In 1800, Alessandro Volta invented the voltaic pile, the first true battery. It was a stack of alternating zinc and copper discs separated by cardboard soaked in brine, and it produced a steady flow of electrical current. And almost immediately, scientists realized that electricity could be used to tear compounds apart. If you passed an electric current through water, the water decomposed into hydrogen and oxygen. If you passed it through molten salts, you could isolate metals that had never been seen before in their pure form. The person who took this technique furthest, fastest, was a young Englishman named Humphrey Davy. Davy was a fascinating character, charismatic, ambitious, a brilliant lecturer who packed the Royal Institution in London with audiences that included fashionable society ladies as much as serious scientists. He was also reckless in the way that early chemists often were, tasting and inhaling his discoveries with an enthusiasm that would horrify any modern safety officer. He nearly killed himself multiple times inhaling various gases, but his work with electrolysis was nothing short of spectacular. In a single extraordinary week in October 1807, Davy isolated potassium and sodium by passing electric current through molten potash and soda. Potassium was first. He placed a piece of moistened potash on a platinum electrode, connected his enormous battery, and watched as tiny globules of a silvery metal appeared at the negative terminal. The metal was so reactive that it burst into flame on contact with water. Davy was reportedly so excited that he danced around the laboratory. The following week, he did the same thing with soda and isolated sodium. Over the next few years, he went on to isolate barium, strontium, calcium, and magnesium using similar techniques. 6 new elements, all pulled from compounds that people had known about for centuries, but had never been able to break apart. The battery changed everything, and Davy's work raised an interesting question that was starting to nag at chemists. There were now around 40 known elements, and the list was growing every few years. Were there patterns? Were there relationships between these elements? Because some of them clearly resembled each other. Sodium and potassium behaved almost identically. Both were soft, silvery metals that reacted violently with water. Chlorine and iodine were both pungent, reactive substances that formed similar compounds. Was there an underlying order, some kind of system that connected these substances to each other? A few people were starting to think so. In 1817, a German chemist named Johann Wolfgang Dobereiner noticed something curious. He found that certain elements seemed to come in groups of 3, which he called triads. Lithium, sodium, and potassium formed one triad. Calcium, strontium, and barium formed another. Chlorine, bromine, and iodine formed a third. And here's what was really interesting about these triads. The atomic weight of the middle element was very close to the average of the other two. Bromine's atomic weight, for instance, was almost exactly halfway between chlorines and iodines. That couldn't be a coincidence. It suggested that there was some kind of numerical relationship lurking beneath the properties of the elements, some hidden arithmetic connecting them. But Dobereiner's triads were just fragments, just glimpses of a pattern. He couldn't extend the idea to cover all the known elements. It was like finding 3 pieces of a jigsaw puzzle that fit together, and knowing there must be a larger picture, but not being able to see what it was. The full picture would take another 50 years to emerge, and it would require something that chemistry didn't quite have yet: reliable atomic weights. Because if you're going to find numerical patterns among the elements, you need accurate numbers to work with. And in the early 1800s, the numbers were a mess. Different chemists used different scales, different assumptions, different methods. 2 chemists might report completely different atomic weights for the same element, and both would insist they were right. The person who did more than anyone to sort out this confusion was a Swedish chemist named Jöns Jacob Berzelius, and his contribution to our story is one of those quiet, unglamorous achievements that made everything else possible. Berzelius was meticulous. That's the word that comes up again and again when you read about him. Meticulous, careful, obsessively precise. He spent years in his laboratory in Stockholm, methodically determining the atomic weights of element after element, refining techniques, cross-checking results, doing the same experiment over and over until he was confident in the numbers. By the 1820s, he had published atomic weight tables that were remarkably accurate. Some of his values are within a fraction of a percent of the ones we use today, which is extraordinary when you consider the tools he was working with. No electronic balances, no mass spectrometers, just glassware and reagents and an almost superhuman patience. And Berzelius gave us something else that we still use every single day. He's the one who came up with the modern system of chemical symbols. Before him, chemists used all sorts of bizarre shorthand: little circles, crosses, alchemical glyphs. Dalton had his own system of circles, with dots and lines inside them. It was a mess. Berzelius said, "Look, let's just use the first letter or 2 of the element's Latin name. Hydrogen gets H, oxygen gets O, iron gets Fe from ferrum, gold gets Au from aurum. Simple, elegant, universal. You've seen these symbols your entire life, on every periodic table poster, in every chemistry textbook, on the labels of supplements and medications. That's Berzelius. He gave chemistry its alphabet. So now, thanks to Berzelius and a handful of other careful experimentalists, chemists had something they'd never really had before: a reliable list of elements with accurate atomic weights attached to each one. And that meant the hunt for patterns could begin in earnest. Dobereiner's triads had been a tantalizing hint, but the real breakthroughs were still a few decades away. And the path to the periodic table, the actual table, the one you'd recognize, turns out to be one of those stories where several people were circling the same idea at almost the same time. And the question of who gets the credit is genuinely complicated. Let me walk you through it, because it's a wonderful story. The first person who deserves mention is a French geologist named Alexandre-Émile Béguier de Chancourtois. In 1862, he did something really creative. He arranged all the known elements in order of their atomic weights and wrapped them around a cylinder, like a spiral. He called it the telluric screw, after tellurium, which sat near the middle of his arrangement. And here's what was clever about it. When you wrapped the elements around this cylinder with a certain circumference, specifically with a circumference corresponding to 16 atomic weight units, elements with similar properties ended up in vertical columns, stacked above each other. It was a three-dimensional way of showing periodicity, of showing that the properties of elements repeated at regular intervals as you went up in atomic weight. It was a genuinely insightful idea, but almost nobody noticed. Partly because de Champcourtois published it in a geology journal rather than a chemistry journal, which meant the chemists who would have cared most about it never saw it. And partly because the published version didn't even include his diagram. The journal left it out, apparently for cost reasons. So you had this elegant visual idea published without the visual. It's one of those small, almost absurd historical accidents that can bury a good idea for decades. 2 years later, in 1864, an English chemist named John Newlands took a different approach. He arranged the elements by atomic weight and noticed that every eighth element seemed to have similar properties. He called this the law of octaves, borrowing the term from music. Just as the eighth note on a piano scale sounds like a higher version of the first note, the eighth element in his sequence seemed to echo the properties of the first. Lithium, sodium, potassium, there they were again, Duberiner's triad. But now Newlands was saying the pattern extended further. It wasn't just groups of three. It was a repeating cycle. Now, you might think the scientific community would have been excited about this. They were not. When Newlands presented his law of octaves to the Chemical Society of London in 1866, one of the members reportedly asked him whether he'd tried arranging the elements alphabetically to see if that produced any patterns too. It was a devastating put-down, and it basically ended the discussion. The society refused to publish his paper. Newlands was humiliated. And here's the thing that makes this story bittersweet. Newlands was onto something real. His law of octaves was imperfect. It broke down for heavier elements, and he sometimes had to squeeze two elements into the same slot to make it work. But the core insight, that elemental properties repeat periodically, was absolutely correct. He was just a few years too early, and his presentation wasn't quite rigorous enough to convince the skeptics. Years later, after the periodic table became famous under someone else's name, Newlands would fight for recognition, and eventually, the Royal Society did award him a medal in 1887. But by then, the glory had gone elsewhere. So where did it go? Well, this is where we meet the two people most associated with the periodic table, and their story is one of the great priority disputes in the history of science. The first is a German chemist named Lothar Meyer. The second is a Russian chemist named Dmitri Mendeleev. And if you only know one name from the history of the periodic table, it's almost certainly Mendeleev. Let's talk about Meyer first, because he tends to get overlooked, and that's not entirely fair. Lothar Meyer was a careful, methodical scientist, a bit like Berzelius in temperament. In 1864, he published a textbook that included a table of about half the known elements arranged by atomic weight, with elements of similar properties grouped together. It was a partial periodic table, and it showed genuine insight. Later, around 1868 or 1869, Meyer produced a more complete version, along with a beautiful, graph-plotting atomic volumes against atomic weights that showed a clear wave-like pattern, peaks and valleys repeating at regular intervals. It was compelling visual evidence for periodicity. But Meyer was cautious. He sat on his more complete table for a while, refining it, and didn't publish it until 1870. And that delay cost him, because in March of 1869, Dmitri Mendeleev had already gone public. Mendeleev, Let me tell you about Mendeleev, because he's one of the most fascinating characters in the history of science. Born in Tobolsk, Siberia, in 1834, the youngest of somewhere between 14 and 17 children. The records aren't entirely clear. His father went blind and lost his teaching position. His mother ran a glass factory to support the family, and when that factory burned down, she essentially walked her youngest son across Russia to get him into university. She died shortly after he was admitted. Think about that determination, that sacrifice. Mendeleev carried it with him his entire life. He was brilliant and difficult and wildly ambitious. He had this enormous mane of hair that he refused to cut more than once a year, which gave him a distinctive, almost wild appearance. He was passionate about Russian industry, about education, about modernizing his country's economy. He wrote a textbook on chemistry, Principles of Chemistry, that became one of the most influential chemistry textbooks ever published. And it was while writing that textbook that he stumbled onto the periodic law. The story, as Mendeleev later told it, goes something like this. He was trying to organize the chapters of his textbook and struggling with how to present the elements in a logical sequence. He wrote the properties of each element on a separate card, 63 elements, 63 cards, and began arranging and rearranging them, looking for patterns. He later claimed that the final arrangement came to him in a dream, that he fell asleep exhausted and saw in his sleep a table where all the elements fell into place. He woke up and immediately wrote it down. Now, the dream story might be a bit of romantic embellishment. Mendeleev was not above self-mythologizing, but what's undeniable is the result. On March 6, 1869, a colleague presented Mendeleev's table to the Russian Chemical Society. The table arranged the elements by atomic weight in rows, with elements of similar properties aligned in columns. And it was good. It was really good. But here's what made Mendeleev's table different from everyone else's attempts, and this is the part that I find genuinely thrilling. It's the thing that separates a clever observation from a truly great scientific achievement. Mendeleev had the audacity to leave gaps. When his arrangement didn't quite work, when an element seemed to be missing from a spot where the pattern said one should exist, Mendeleev didn't force a bad fit. He didn't abandon the pattern. He said, "There must be an element here that we haven't discovered yet." And then he predicted the properties of those missing elements. He predicted their atomic weights, their densities, their melting points, the types of compounds they would form. He gave them provisional names: eka-boron, eka-aluminium, eka-silicon, using the Sanskrit prefix eka, meaning one, to indicate they were one position away from known elements. Think about the confidence that requires. You're telling the entire scientific community, "I'm so sure my table is right, that I'm predicting elements nobody has ever seen." If those predictions turn out to be wrong, your career is finished. You're a laughingstock. But Mendeleev believed in the pattern. And then the elements started showing up. In 1875, a French chemist named Paul-Émile Lecoq de Boisbaudran discovered a new element in a zinc ore from the Pyrenees. He named it gallium, after Gallia, the Latin name for France. And when he measured its properties, its density, its melting point, its atomic weight, they matched Mendeleev's predictions for eka-aluminium almost exactly. There's a wonderful detail in this story. Lecoq de Boisbaudran initially reported gallium's density as 4.7 grams per cubic centimeter, but Mendeleev, working from his theoretical predictions, wrote to him and said, "No, I believe you'll find the density is closer to 5.9. Lecoq de Boisbaudran rechecked his measurements, purified his sample more carefully, and found that Mendeleev was right. The Russian chemist, who had never held a speck of gallium in his life, knew its density better than the man who discovered it. That's the power of a good theory. Then, in 1879, Lars Fredrik Nilsson, in Sweden, discovered scandium, Mendeleev's Eka boron. Its properties matched the predictions beautifully, and in 1886, Clemens Winkler in Germany discovered germanium, Eka silicon. Again, the match was almost uncanny. Mendeleev had predicted germanium's atomic weight would be about 72. It turned out to be 72.6. He predicted its density would be about 5.5. It was 5.47. He predicted it would form a compound with chlorine having a boiling point near 100 degrees Celsius. The actual boiling point was 86 degrees. Each confirmed prediction was like a hammer blow driving the periodic table deeper into the bedrock of accepted science. By the mid-1880s, the debate was essentially over. The periodic table wasn't just a convenient way to organize elements. It was revealing something fundamental about the structure of matter, some deep principle that determined why elements had the properties they did. Nobody yet knew what that principle was. That understanding would require the discovery of subatomic particles, which was still a decade or two away. But the pattern was undeniable. And poor Lothar Meyer, who had independently arrived at essentially the same arrangement. He received some recognition, and today historians generally credit both men. But Mendeleev's willingness to make bold predictions, to stick his neck out and say, "Here is what we will find," gave his version of the table a power that Meyer's more cautious approach simply couldn't match. There's a lesson in that about the difference between seeing a pattern and trusting it enough to bet your reputation on it. Now, while Mendeleev's table was conquering the scientific world, there was a quiet problem lurking at its edges. A few elements didn't quite fit. Their atomic weights put them in the wrong columns, next to elements they didn't resemble at all. Mendeleev handled this by simply insisting that the atomic weights must be wrong, and in some cases he turned out to be right. The weights were revised, and the elements fell into place. But in other cases, the problem was more stubborn. Tellurium and iodine, for instance. By atomic weight, tellurium should come after iodine, but by its chemical properties, tellurium clearly belonged in the same column as sulfur and selenium, while iodine belonged with chlorine and bromine. Mendeleev swapped them, putting properties ahead of atomic weight, and it nagged at him. It was a crack in the foundation, a hint that atomic weight wasn't quite the right organizing principle. The right principle, atomic number, the number of protons in the nucleus, wouldn't be understood until the early 20th century, and the person who would finally put it on solid experimental footing was a young English physicist named Henry Moseley, whose story is both brilliant and heartbreaking. Moseley was born in 1887 into a family that practically breathed science. His father was a naturalist and professor of anatomy at Oxford, though he died when Henry was just 4 years old. His grandfather had been a renowned mathematician and physicist. So there was this deep intellectual lineage running through the family, and young Henry seemed destined to carry it forward. He studied at Eton, then went up to Oxford, and by the time he was in his early 20s, he'd made his way to Manchester to work under Ernest Rutherford. And if you know anything about early 20th century physics, you know that Rutherford's lab in Manchester was basically the center of the universe. This was the place where the atom was being cracked open, where the very idea of what matter is made of was being rewritten in real time. Rutherford had already proposed his nuclear model of the atom by 1911, the idea that most of an atom's mass is concentrated in a tiny, dense nucleus at the center, with electrons orbiting around it like planets around a sun. That model was revolutionary, but it raised an immediate question. What determines where an element sits in the periodic table? Mendeleev had used atomic weight, and that worked almost perfectly, but not quite. Those nagging exceptions like tellurium and iodine kept whispering that something deeper was going on. A Dutch physicist named Antonius van den Broek had suggested in 1911 that the charge on the nucleus, the number of positive charges, might be the real ordering principle. But it was Moseley who proved it. Here's what he did, and it's beautifully elegant. In 1913 and 1914, Moseley systematically bombarded different elements with cathode rays, high-energy electrons, and measured the X-rays that each element emitted. Now, every element, when you hit it with enough energy, gives off X-rays at characteristic frequencies. Moseley measured those frequencies with extraordinary precision, element after element, working his way through the periodic table. And what he found was stunning in its simplicity. When he plotted the square root of the X-ray frequency against the position of each element in the periodic table, he got a nearly perfect straight line. Not a wiggly curve, not a rough trend, a clean, beautiful, unmistakable straight line. Think about what that means. It meant that there was some fundamental quantity increasing by exactly 1 unit as you moved from one element to the next in the periodic table. That quantity, Moseley argued, was the nuclear charge, the number of protons in the nucleus. He called it the atomic number. And just like that, the periodic table had a new foundation. It wasn't atomic weight that determined an element's identity and its place in the table. It was atomic number. The tellurium-iodine problem. Solved instantly. Tellurium has atomic number 52. Iodine has atomic number 53. By atomic number, they're in the right order. The fact that tellurium happens to be slightly heavier than iodine is just a quirk of how many neutrons each element's atoms carry. It has nothing to do with their fundamental chemical identity. Moseley's work did something else remarkable. By plotting that straight line, he could see where there were gaps, places where an element should exist but hadn't been discovered yet. He identified several missing atomic numbers, and this gave experimentalists specific targets to hunt for. It was Mendeleev's predictive trick all over again, but now with even more precision and theoretical backing. And here's the part that makes you want to set down whatever you're holding and just sit with it for a moment. Henry Moseley was 27 years old when he published this work. 27. He had essentially solved one of the deepest puzzles in chemistry, given the periodic table its true mathematical backbone, and opened up entirely new avenues in atomic physics. Rutherford himself said that Moseley's work was one of the most brilliant pieces of research he'd ever encountered. There was talk, serious talk, that Moseley would almost certainly receive a Nobel Prize. He was that good, that young, and that clearly on a trajectory toward greatness. Then the First World War broke out. Moseley volunteered for the Royal Engineers and was deployed to Gallipoli in 1915. On August 10th of that year, during the Battle of Sari Bair, he was shot through the head by a sniper. He was 27 years old. The loss was so devastating to British science that it's often cited as one of the reasons the British government later adopted policies to keep prominent scientists out of combat roles. Isaac Asimov once called Moseley's death the most costly single death of the war to mankind generally. Whether or not you agree with that specific ranking, the point stands. Here was a mind that had already reshaped our understanding of matter, and we can only wonder what else he might have done with another 40 or 50 years. So let's sit with what the periodic table looked like after Moseley. By the early 20th century, you had this beautiful grid of elements, organized by atomic number, with clear families running down the columns, the alkali metals on the left, the halogens near the right, the noble gases at the far right. But there was a whole section of the table that was causing headaches, and it's worth talking about because it reveals just how tricky nature can be when you try to organize it neatly. I'm talking about the rare earth elements, the lanthanides. These are the elements starting with lanthanum, atomic number 57, and running through lutetium, atomic number 71. If you've ever looked at a periodic table, you've probably noticed that strange floating row at the bottom, almost like a footnote. That's the lanthanides, along with the actinides below them. And the reason they're pulled out like that is because they simply don't fit neatly into the main grid. All 15 lanthanides have remarkably similar chemical properties. They're all silvery metals. They all form similar compounds. They all tend to exist in a +3 oxidation state. Chemically, they're almost interchangeable, which made them incredibly difficult to separate from one another, and even harder to figure out where exactly each one belonged in the table. For decades, the rare earths were a thorn in the side of anyone trying to build a clean, logical periodic table. Mendeleev himself struggled with them. Some chemists argued there might be far more rare earth elements than anyone suspected, maybe dozens of them. Others thought some of the supposed rare earths were actually mixtures that hadn't been properly separated. The confusion was real and deep, and it wasn't fully resolved until the development of quantum mechanics in the 1920s and 30s, when physicists finally understood why these elements are so similar. It comes down to electron configuration, specifically, the filling of the 4f electron orbitals. As you add electrons to these inner orbitals, the outer electron shell, the one that determines most of an element's chemical behavior, barely changes. So you get this long parade of elements that look almost identical from a chemical standpoint, even though their atomic numbers are marching steadily upward. And this brings us to something really lovely about the periodic table, which is that its shape, its actual physical layout on the page, is a direct reflection of quantum mechanics. The two tall columns on the left correspond to the filling of s orbitals. The block of 10 columns in the middle corresponds to d orbitals. The 6 columns on the right correspond to p orbitals. And those 2 floating rows at the bottom correspond to f orbitals. The table's architecture encodes the quantum mechanical structure of the atom. Mendeleev had no idea about any of this when he arranged his cards by atomic weight and chemical properties in 1869. He was working purely from observed patterns, and yet the structure he built turned out to map almost perfectly onto a theory of atomic structure that wouldn't exist for another 50 years. That's one of those things that gives you chills if you think about it long enough. Now, while physicists were unraveling the quantum structure of atoms, chemists were still busy discovering new elements to fill the remaining gaps in the table. And some of these discoveries came with their own dramatic stories. Take element 72, hafnium. By the early 1920s, Moseley's work had made it clear that there should be an element with atomic number 72, and scientists were racing to find it. A French chemist named Georges Urbain claimed in 1911 that he'd found it among the rare earth minerals, and he called it celtium. But here's where it gets interesting. Niels Bohr, the great Danish physicist, used his new quantum theory of electron shells to predict that element 72 should not be a rare earth at all. It should be a transition metal, chemically similar to zirconium. If Bohr was right, you wouldn't find it in rare earth ores. You'd find it in zirconium minerals. In 1923, two scientists working in Bohr's Institute in Copenhagen, Dirk Koster, a Dutch physicist, and George de Hevesy, a Hungarian chemist, followed Bohr's prediction and examined zirconium ores using X-ray spectroscopy, Moseley's own technique. And there it was. Element 72, right where Bohr said it would be. They named it hafnium, after Hafnia, the Latin name for Copenhagen. Urbain's celtium turned out to be a mixture of already known rare earths. The discovery was a beautiful vindication of quantum theory. The new physics wasn't just explaining known elements, it was predicting where unknown ones would be found and what they'd be like. It was Mendeleev's game all over again, played with even more powerful tools. But not all element discoveries were so clean. Some were mired in controversy, false claims, and nationalist rivalry. And as scientists pushed into the far reaches of the periodic table, elements with higher and higher atomic numbers, the discoveries became stranger, more difficult, and more consequential. Because those heavy elements, the ones beyond uranium at atomic number 92, don't exist in nature in any meaningful quantity. To find them, you don't dig them out of the ground. You have to make them. And the story of how scientists learned to create entirely new elements, atoms that had never existed on Earth before, is tangled up with one of the most transformative and terrifying technological developments in human history. It starts in the 1930s, in laboratories in Rome and Berlin and Berkeley, with a handful of physicists who were trying to understand what happens when you fire neutrons at the heaviest atoms you can find. Uranium. Element 92. The last naturally occurring element in any significant abundance. And the question these physicists were asking seemed almost innocently simple. What happens if you add one more neutron to a uranium nucleus? Can you push past 92? Can you build element 93? The person who kicked this whole effort into high gear was Enrico Fermi, working in Rome. Fermi was one of those rare physicists who was brilliant at both theory and experiment, which is unusual. Most people lean one way or the other. He'd already done landmark theoretical work on beta decay, and by 1934, he'd turned his attention to bombarding elements with neutrons. His idea was systematic and almost brute force in its elegance. Take every element you can get your hands on, hit it with neutrons, and see what happens. His team in Rome worked their way through the periodic table, element by element. When they got to uranium, things got interesting. They detected radioactive products that didn't seem to match any known element lighter than uranium. Fermi cautiously, and this is important, cautiously, suggested they might have created elements 93 and 94. Transuranic elements, elements beyond uranium. The press was less cautious. Italian newspapers ran with it, and there was even a story that Fermi's work was presented to Mussolini as a great Italian achievement. But Fermi himself had reservations. He couldn't definitively identify what he'd made. And here's where one of the most remarkable scientific detectives in history enters the story. Ida Nodak, a German chemist, read Fermi's 1934 paper and pointed out something that nobody else was willing to consider. She suggested that maybe Fermi hadn't created heavier elements at all. Maybe the uranium nucleus, when hit by a neutron, had actually broken apart into much lighter fragments. She was proposing nuclear fission, essentially, 4 years before anyone else took the idea seriously, and almost everyone ignored her. The physics community dismissed her suggestion as implausible because no one had ever seen a heavy nucleus split in two, and the prevailing models didn't predict it. There was also, let's be honest, a gender component. Nodak was a woman in a field dominated by men, and her earlier claim to have discovered element 43, which she called Mesurium, had been disputed and was viewed with skepticism, so her fission hypothesis was set aside. It's one of those moments in science history that makes you wince, because she was right. The work continued, though, most intensely in Berlin. Lise Meitner, Otto Hahn, and Fritz Strassmann were the key team. Meitner was an Austrian-born physicist who had been working in Berlin for decades. She was one of the first women to earn a doctorate in physics from the University of Vienna, and she'd built a formidable career in radioactivity research. Hahn was a chemist, meticulous, and skilled at radiochemical analysis. They'd been collaborating for 30 years. But in 1938, the political situation made everything enormously more complicated. Meitner was Jewish by birth, and after Germany annexed Austria in March of that year, she lost her Austrian citizenship and its protections. She had to flee. With the help of colleagues, she escaped to Sweden, crossing the border with little more than 10 marks in her purse and a diamond ring that a friend had given her in case she needed to bribe a guard. She ended up in Stockholm, somewhat isolated, but she stayed in close contact with Hahn by letter. Back in Berlin, Hahn and Strassmann continued the neutron bombardment experiments through the fall of 1938. And in December, they got a result that baffled them. When they bombarded uranium with neutrons, the chemical analysis showed barium among the products. Barium, element 56. That's not a transuranic element. It's nowhere near uranium on the periodic table. It's roughly half the mass of uranium. Hahn was a superb chemist, and he trusted his analysis, but the result made no physical sense to him. He wrote to Meitner in Stockholm, essentially saying, "We keep finding barium, and we can't explain it. Can you think of any physics that would account for this?" And this is where Meitner's contribution becomes extraordinary. She was visiting friends in the Swedish countryside over Christmas when Hahn's letter arrived. Her nephew, Otto Robert Frisch, who was also a physicist, happened to be visiting too. They went for a walk in the snow, Frisch on skis, Meitner on foot, keeping up despite being in her late 50s, and they worked through the problem together. Meitner recalled Bohr's model of the nucleus as something like a liquid drop. If a uranium nucleus absorbed a neutron and became unstable, it might elongate, wobble, and eventually pinch apart into two smaller nuclei, like a drop of water splitting in two. She and Frisch did a quick calculation right there, sitting on a tree trunk in the snow, and realized that the two fragment nuclei would have less total mass than the original uranium nucleus plus the neutron. The missing mass, converted to energy via Einstein's famous equation, would be enormous, about 200 million electron volts per fission event. That's a staggering amount of energy from a single atom. Frisch went back to Copenhagen and confirmed the phenomenon experimentally within weeks. He borrowed the term fission from biology, where it describes cell division. Hahn and Strassmann published their chemical findings in January 1939. Meitner and Frisch published the physical interpretation almost simultaneously. And just like that, the world changed. Think about what that means. Every uranium atom is a tiny reservoir of energy, and if you can split enough of them, the energy release is beyond anything chemistry can achieve. A single kilogram of uranium undergoing complete fission releases roughly the same energy as 20,000 tons of TNT. The implications were immediately obvious to every physicist who read those papers, and they were terrifying. Now, here's something that still stings. When the Nobel Prize for the discovery of nuclear fission was awarded in 1944, it went to Otto Hahn alone. Meitner was excluded. Strassmann was excluded. The reasons are complex: wartime politics, the Nobel Committee's internal dynamics, and arguably a failure to properly credit the physics alongside the chemistry. Meitner never publicly complained, but the omission is widely regarded today as one of the most glaring injustices in Nobel history. Element 109, meitnerium, was eventually named in her honor in 1997, long after her death. It's a small consolation for someone who deserved so much more recognition in her lifetime. But let's come back to the periodic table itself, because fission opened a door. If you could split atoms, could you also build them? Could you actually create those transuranic elements that Fermi had been chasing? The answer came from Berkeley, California, from a team led by Edwin McMillan and Philip Abelson. In 1940, they bombarded uranium with neutrons at the Berkeley cyclotron, a particle accelerator that Ernest Lawrence had pioneered. And this time, they carefully tracked the decay products. They found that uranium-238, when it captured a neutron, became uranium-239, which then underwent beta decay. And beta decay, remember, is when a neutron in the nucleus converts into a proton, emitting an electron. That means the atomic number goes up by 1. Uranium, element 92, became element 93. They named it Neptunium, after Neptune, the next planet beyond Uranus, since uranium had been named after Uranus. There's a lovely logic to that naming convention, and it continued. Within a year, Glenn Seaborg and his team at Berkeley identified element 94, produced by the beta decay of Neptunium. They named it plutonium, after Pluto, the next planet out, or what was then considered the next planet. Pluto's had a rough time with its planetary status since then, but plutonium's place on the periodic table is secure. Seaborg is a figure worth lingering on because his impact on the periodic table was enormous. He was a Nebraska-born chemist, tall, quiet, methodical, and he would go on to be involved in the discovery of 10 elements. 10. That's more than any other person in history. But his most important conceptual contribution might have been rearranging the periodic table itself. As his team at Berkeley produced and studied the transuranic elements, neptunium, plutonium, and then americium and curium in the mid-1940s, Seaborg noticed something. These new elements didn't behave chemically the way you'd expect if they were simply heavier versions of the transition metals. They were being placed in the main body of the table, under rhenium and osmium and so on, but their chemistry didn't match. They were more similar to each other, and more similar to the lanthanides, than to any transition metal. Seaborg had a radical idea. He proposed that just as the lanthanides formed a separate series where the 4f electron shell was being filled, there must be an analogous series, an actinide series, where the 5f shell was being filled, starting at actinium, element 89. This would mean pulling a whole row of elements out of the main body of the table and placing them below the lanthanides, creating that second detached row at the bottom that you see on every periodic table today. His colleagues told him it was career suicide. Publishing such a fundamental revision, they said, would make him look foolish. But Seaborg trusted his chemical evidence, and he was right. The actinide concept explained the chemistry of uranium, neptunium, plutonium, and all the elements that followed. It was the last major structural revision to the periodic table's layout, and it happened in 1945. Meanwhile, of course, plutonium had become something far more than a scientific curiosity. The Manhattan Project had recognized that plutonium-239 was fissile. It could sustain a chain reaction, and it became the core material for the bomb dropped on Nagasaki in August 1945. Element 94, barely 5 years old, had already been manufactured in quantities measured in kilograms inside nuclear reactors and shaped into the heart of a weapon that killed tens of thousands of people. There's no separating the story of the transuranic elements from the story of nuclear weapons. The periodic table, this beautiful intellectual framework for understanding matter, was now entangled with the capacity for destruction on an unimaginable scale. The physicists who had spent the 1930s chasing neutrons and puzzling over barium in their lab results were now grappling with moral questions that had no clean answers. But the element building didn't stop with the war. If anything, it accelerated. Seaborg's group and others pushed further up the periodic table through the late 1940s and 1950s, creating elements 95 through 101, americium, curium, berkelium, californium, einsteinium, fermium, and mendeleevium. Each one was harder to make than the last, produced in smaller and smaller quantities, and with shorter and shorter half-lives. Some of these elements were first detected in the fallout from thermonuclear weapon tests. Einsteinium and fermium were discovered in the debris from the first hydrogen bomb test, Ivy Mike, in 1952. Scientists analyzing coral samples from the blast site found atoms that shouldn't exist in nature, atoms that had been forged in the unimaginable neutron flux of a thermonuclear explosion. There's something deeply strange about discovering new elements in the ashes of a weapon designed to obliterate cities. And yet, some of these elements found peaceful, even mundane applications. Americium-241, element 95, is in the smoke detector that's probably sitting on your ceiling right now. A tiny amount of it emits alpha particles that ionize the air inside the detector, creating a small current. When smoke enters the chamber, it disrupts that current, and the alarm goes off. You're sleeping under a transuranic element tonight, an atom that doesn't exist in nature, made in a nuclear reactor, sitting in a small plastic disc above your head, quietly keeping you safe. That's the periodic table at work in the most literal, everyday sense. By the late 1950s, the race to create ever heavier elements had become geopolitical. American and Soviet laboratories were competing fiercely, and the disputes over priority, who made which element first, would drag on for decades. The laboratories at the center of this rivalry were Berkeley in California and Dubna, about 100 kilometers north of Moscow. And the element that became the most bitterly contested was element 104, the first element beyond the actinide series. The Americans said they'd made it and wanted to call it Rutherfordium. The Soviets said they'd made it first and called it Kurchatovium, after Igor Kurchatov, the father of the Soviet nuclear program. Both sides published papers. Both sides questioned each other's evidence, and the international chemistry community was caught in the middle, unable to decide who deserved credit. And this wasn't just academic pride. Naming an element is one of the highest honors in science. It's permanent. It goes on every periodic table printed from that moment forward, in every classroom, every textbook, every country on Earth. So the stakes felt enormous, even if, to an outsider, the whole thing might have seemed a little absurd. Two superpowers with enough nuclear weapons to end civilization, arguing over what to call an atom that vanishes in seconds. The dispute over element 104 was just the beginning. Elements 105 and 106 sparked their own battles. The Americans proposed hahnium for 105 after Otto Hahn. The Soviets proposed Niels Bohrium after Niels Bohr. For 106, the Americans eventually wanted Seaborgium after Glenn Seaborg, who was still alive at the time, which added another layer of controversy because there was an informal tradition that you didn't name elements after living people. The whole mess became known as the Transfermium Wars, and if that sounds dramatic, well, it was. It consumed scientific committees, generated reams of correspondence, and soured relationships between researchers who, in a different political climate, might have been collaborators instead of rivals. It took an international body called IUPAC, the International Union of Pure and Applied Chemistry, years to sort it out. They formed a working group, the Transfermium Working Group, in the 1980s, and the final, agreed-upon names for elements 104 through 109 weren't officially settled until 1997. Think about that. Nearly 3 decades of argument. Element 104 became Rutherfordium, which was what the Americans had wanted. Element 105 became dubnium, a nod to the Soviet laboratory. Element 106 did become Seaborgium, making Glenn Seaborg the first person to see his own name on the periodic table while still alive. He reportedly said it was the greatest honor he'd ever received, which, coming from a man who'd won the Nobel Prize and advised presidents, tells you something about what the periodic table means to chemists. But here's what's really interesting about this whole era. Beyond the politics, the science itself was getting harder. Fundamentally, physically harder. Every new element you try to create is heavier than the last, and heavier means less stable. The atoms you're making don't stick around. Element 104 has a half-life measured in seconds. By the time you get to the elements in the 100 teens, you're talking about atoms that exist for fractions of a second, sometimes milliseconds, sometimes microseconds. You might make one atom, maybe 2, in weeks of bombardment, and it decays almost instantly. So how do you even know you made it? This is where the experimental ingenuity becomes really beautiful. Let me walk you through how superheavy element synthesis actually works, because it's one of those things that sounds impossible until you understand the cleverness behind it. You start with a target, a thin foil of some heavy element, maybe lead or bismuth or californium. Then you accelerate lighter ions, like calcium or chromium ions, in a particle accelerator, a cyclotron usually, and you slam them into that target at enormous speeds. Most of the time, the projectile ions just scatter off the target atoms or break them apart. But very, very occasionally, the nuclei actually fuse together. The protons and neutrons from the projectile merge with the protons and neutrons of the target, and for a fleeting instant, you have a new, heavier nucleus, a new element. But that nucleus is born in an incredibly excited state. It's vibrating, it's unstable, it's got too much energy. It needs to shed that energy fast, or it'll just fly apart. Usually it does this by spitting out a few neutrons, what physicists call a hot fusion reaction, or sometimes in cold fusion reactions, which have nothing to do with the controversial cold fusion energy claims from 1989, by the way. Totally different thing. The nucleus is formed with less excitation energy and emits just 1 or 2 neutrons and a gamma ray. The nucleus that survives this initial de-excitation is your new element. But it's still unstable. It starts decaying, usually through alpha decay, spitting out a helium nucleus, which means it loses 2 protons and 2 neutrons, so it transforms into a slightly lighter element. And then that daughter nucleus decays too, and the next one, and the next one, creating a chain of alpha decays that you can detect. Each decay releases a characteristic amount of energy, and by measuring those energies and the time intervals between them, you can work backward and figure out what the original atom was. It's like identifying a firework by the pattern of sparks it leaves as it falls. You never actually see the original atom sitting there. You see its death, and from the way it dies, you deduce what it was. This technique is called decay chain analysis, and it's the backbone of superheavy element discovery. The detectors involved are extraordinary. Silicon semiconductor detectors that can pinpoint exactly where a single atom implants itself after flying out of the target, and then record every subsequent decay event at that exact spot. The whole setup is designed to catch something that happens maybe once in a billion collisions. Now, the laboratory that really perfected this approach in the 1980s and 1990s was the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. And their leader was a physicist named Peter Armbruster, working alongside Gottfried Munzenberg. Between 1981 and 1996, the Darmstadt team discovered elements 107 through 112. That's 6 new elements from a single lab, which is a remarkable run. They used cold fusion reactions, slamming various projectile ions into lead and bismuth targets, and they developed increasingly sensitive detection systems to catch the tiny handful of atoms produced. Element 110 was synthesized in 1994 and eventually named Darmstadtium, after the city. Element 111, discovered in 1994 as well, became Roentgenium after Wilhelm Röntgen, who discovered X-rays. Element 112, first created in 1996, was named Copernicium after Copernicus. And here's a small detail I love. The team produced exactly 1 atom of copernicium in their initial experiment. 1 atom. They identified it by its decay chain, watched it alpha decay through a sequence of known daughter nuclei, and from that single event, they could say with confidence that they'd created element 112, 1 atom, and it was enough. But cold fusion reactions were hitting a wall. As you try to make heavier and heavier elements this way, the probability of fusion drops off dramatically. The cross-sections, which is the physicist's way of describing how likely the reaction is, become vanishingly small. You could run your accelerator for months and not produce a single atom. So the field needed a new approach. And that new approach came from Dubna, the Russian laboratory that had been in the game since the very beginning of the transfermium wars. Specifically, it came from a physicist named Yuri Oganessian. If Mendeleev is the father of the periodic table, Oganessian might be called the father of its modern frontier. He'd been working on superheavy element synthesis since the 1960s, and by the late 1990s, he championed a different strategy: hot fusion reactions using calcium-48 as the projectile. Calcium-48 is a remarkable isotope. It has 20 protons and 28 neutrons, both of which are magic numbers in nuclear physics, numbers that correspond to completely filled nuclear shells, making the nucleus exceptionally stable and tightly bound. When you fire calcium-48 at an actinide target like plutonium, curium, or californium, you get a compound nucleus with a surprisingly good chance of surviving long enough to shed its excess energy and settle into a new superheavy element. The cross-sections are orders of magnitude larger than what the cold fusion approach could achieve at these masses. It was a game changer. Starting in 2000, Oganessian's team at Dubna working in collaboration with scientists from Lawrence Livermore National Laboratory in California, former Cold War rivals, now partners, began producing elements 113 through 118. Element 114, flerovium, was first synthesized in 1998 and confirmed in subsequent experiments. Element 115, moscovium, followed. Element 116, livermorium, named after Livermore, a nice gesture of collaboration. Element 117, tennessine, named after Tennessee, where Oak Ridge National Laboratory provided the berkelium target material. And element 118, oganesson, named after Yuri Oganessian himself, making him only the second person in history to have an element named after him while still alive. Think about the poetry of that for a moment. The periodic table that Mendeleev sketched out in 1869, with its gaps and predictions, now stretches all the way to element 118. The seventh row is complete. Every single box is filled, and the man whose name sits in the last box of that row is still alive, still working, still thinking about what comes next. But here's the thing that makes the super-heavy elements so fascinating from a purely scientific standpoint, beyond the bragging rights and the naming ceremonies. These elements test our understanding of physics itself. When you have a nucleus with 118 protons, the electrons orbiting that nucleus are moving at a significant fraction of the speed of light. At those speeds, relativistic effects become important. The electrons' masses increase, their orbitals contract, and the chemical properties of the element can be dramatically different from what you'd predict based on its position in the periodic table. Oganesson is a perfect example. It sits in the column of noble gases: helium, neon, argon, krypton, xenon, radon, and then oganesson at the bottom. You'd expect it to be a gas with very low reactivity, like its lighter cousins. But theoretical calculations suggest that oganesson might actually be a solid at room temperature, if you could ever make enough of it to tell. Its electron cloud may be so distorted by relativistic effects that it doesn't behave like a noble gas at all. Some models predict it might even be somewhat reactive. We can't test this experimentally yet because we've only ever made a few atoms of it, and they decay in less than a millisecond. But the predictions alone are extraordinary. They suggest that at the very bottom of the periodic table, the neat patterns that Mendeleev discovered start to blur and warp, bent by the strange physics of relativity. And this connects to one of the most tantalizing ideas in nuclear physics: the island of stability. Back in the 1960s, theorists predicted that certain combinations of protons and neutrons would form especially stable superheavy nuclei, with half-lives potentially millions of times longer than their neighbors. The magic numbers for this predicted island are around 114 protons and 184 neutrons. We've reached 114 protons with flerovium, but the isotopes we've made so far have fewer neutrons than the predicted sweet spot. Still, there are hints. Flerovium isotopes do live longer than their neighbors, some for nearly a second, which in this realm is an eternity. It's as if we've reached the shoreline of the island, but haven't yet found its peak. The search for the island of stability is one of the driving motivations behind the next generation of superheavy element experiments. New facilities are being built or upgraded around the world. The Superheavy Element Factory at Dubna, which came online in 2019, can deliver calcium-48 beams 10 times more intense than before. Similar efforts are underway in Japan at Riken, where a team led by Kosuke Morita discovered element 113, nihonium. the first element discovered in Asia. And in Germany, the FAIR facility at Darmstadt promises even more powerful beams. The goal isn't just to add more elements to the table, although elements 119 and 120 are actively being pursued. The deeper goal is to understand the limits of matter itself. Is there a point where no nucleus can hold together, no matter how many neutrons you pack around the protons? Or does the island of stability extend further than we think, harboring atoms that might last long enough to study their chemistry, to actually learn what a superheavy element does when it meets other atoms? And while all of this cutting-edge physics is happening at the far edge of the periodic table, something equally fascinating has been unfolding in how we understand the elements that were already there. Because the periodic table isn't just a list of elements arranged by atomic number. It's a map of electron behavior. And in the 20th and 21st centuries, our understanding of that behavior has become so much richer, so much stranger, and so much more beautiful than anyone in the 19th century could have imagined. Think about what Mendeleev had when he arranged his cards on that table in 1869. He had atomic weights, he had valence, how many bonds an element like to form. He had observable properties like melting point, density, reactivity, and from those clues alone, he built something extraordinary. But he didn't know why the pattern existed. He couldn't explain why every 8th element or every 18th element seemed to echo the behavior of the one before it. The periodicity was visible, but the mechanism behind it was hidden. It took quantum mechanics to reveal that mechanism, and when it did, the periodic table transformed from an empirical chart, something that worked because it worked, into a theoretical map that told you exactly where you were in the architecture of the atom. Here's how to think about it. Every element has its electrons arranged in shells and subshells, and those subshells come in 4 flavors labeled S, P, D, and F. You've heard those letters before in this story. We talked about F orbitals when we discussed the lanthanides and D orbitals when we talked about transition metals. But let's slow down and really sit with what those letters mean, because they're the key to the entire shape of the periodic table. The S subshell can hold 2 electrons. The P subshell can hold 6. The D subshell can hold 10. And the F subshell can hold 14. Now look at the periodic table. The first 2 columns on the left, hydrogen, lithium, sodium, potassium, and their partners, that's the S block. 2 columns wide, because S holds 2 electrons. The 6 columns on the right side, from boron's group over to the noble gases, that's the P block. 6 columns wide, because P holds 6. The 10 columns of transition metals in the middle, that's the D block. 10 columns, and that double row of lanthanides and actinides usually printed below the main table, that's the F block. 14 columns wide, 2, 6, 10, 14. The width of each block is literally the capacity of the corresponding subshell. The table's shape isn't arbitrary. It's a portrait of quantum mechanics. And this is where it gets interesting, because once you see the table this way, you start to understand not just what the elements do, but why they do it. Why is sodium so reactive? Because it has 1 lonely electron in a new S subshell, far from the nucleus, barely held on, desperate to be given away. Why is chlorine so reactive? Because it has 5 electrons in a P subshell that wants 6. It's 1 electron short of a full set, and it will rip that electron from almost anything. Why are the noble gases inert? Because their outer P subshell is completely full. There's no room to add an electron, and no incentive to lose one. Everything is satisfied. It's the electronic equivalent of a perfectly packed suitcase. Nothing else fits, and nothing wants to come out. But here's the thing. That tidy picture, the one you find in introductory chemistry textbooks, starts to get complicated when you look more carefully. And the complications are genuinely fascinating, because they reveal that the periodic table isn't quite as neat as it looks on a poster. Take copper, for instance. Element 29. If you follow the standard filling order for electron shells, the Aufbau principle from the German word for building up, copper should have a configuration where its 3d subshell holds 9 electrons and its 4s subshell holds 2. But it doesn't. What actually happens is that one of those 4s electrons drops down into the 3d subshell, giving copper a completely full 3d10 and a lone 4s1. Why? Because a fully filled subshell has a special stability. There's an energetic bonus that comes from having all 10 d orbital slots occupied. The atom is willing to sacrifice the expected configuration for a lower energy, more stable one. Chromium does something similar, preferring a half-filled d subshell of 5 rather than the expected 4. These exceptions used to bother chemists. They seemed like flaws in the system. But they're not flaws. They're the system showing you that it's more subtle than the simplified rules suggest. The Aufbau principle is a guideline, not a law. The real law is that atoms will find whatever electron arrangement gives them the lowest total energy, and sometimes that means breaking the expected pattern. Now, multiply that kind of subtlety across the entire table, and you start to see why modern periodic table scholarship is such a rich field. There are genuine, ongoing debates about where certain elements belong. Hydrogen is the classic example. It sits at the top of group 1, above lithium, because it has one s electron. But hydrogen is nothing like lithium. Lithium is a soft, reactive metal that bursts into flame when you drop it in water. Hydrogen is a gas. In some ways, hydrogen behaves more like a halogen. It can gain an electron to form a negative ion, just like fluorine and chlorine do. Some periodic tables place hydrogen above fluorine in group 17 instead. Others put it in both places. Others float it off on its own, unattached to any group, which honestly might be the most honest representation. Hydrogen is unique. It's the simplest atom, 1 proton and 1 electron, and it doesn't really have a perfect home in the table. Helium raises a similar question. It's universally placed with the noble gases, in group 18, at the top of the column. And that makes sense in terms of chemistry. Helium is inert. It doesn't form compounds under normal conditions. It behaves like a noble gas. But electronically, helium has 2 electrons in a 1s subshell. That makes it an s-block element. If you were arranging the table purely by electron configuration, helium should sit next to hydrogen, above beryllium, in group 2. Some physicists and a few chemists have actually argued for this placement. It's not a crazy idea. It's internally consistent with the organizational logic of the rest of the table. But most chemists resist it because it separates helium from the noble gases, and the whole point of the periodic table is to group elements with similar properties together. So which organizing principle wins? Electron configuration or chemical behavior? The fact that this debate is still alive in the 21st century tells you something important. The periodic table is a human creation, a model, and like all models, it involves choices about what to emphasize. And then there's the question of the F block and where it actually connects to the rest of the table. You know those lanthanides and actinides that are usually printed as a separate island below the main table? That's a convention, not a necessity. It's done mostly because if you inserted them where they technically belong, between groups 3 and 4, the table would be 32 columns wide, and it wouldn't fit nicely on a page or a classroom wall. The 18-column version we're all used to is actually a compromise, a compressed representation. The full, uncompressed table, sometimes called the long form or the 32-column form, shows the F-block elements right where they belong in the flow of atomic numbers. It's wider and harder to print, but it's arguably more honest. And even within this debate, there's a sub-debate about exactly which elements mark the boundaries of the F-block. Do lanthanum and actinium belong in the D-block or the F-block? What about lutetium and lawrencium? This might sound like an arcane argument, but it has real consequences for how we teach chemistry, how we think about electron configurations, and how we categorize the elements at the very boundaries between blocks. In 2021, IUPAC actually convened a project to try to settle the question of Group 3's membership once and for all. Should it be scandium, yttrium, lanthanum, and actinium, or scandium, yttrium, lutetium, and lawrencium? The project examined the evidence from multiple angles: electron configurations, chemical properties, physical properties, and the mathematical structure of quantum mechanics itself. The recommendation, published in a provisional report, favored lutetium and lawrencium in Group 3, which would place lanthanum and actinium at the beginning of the F-block rather than in the D-block. It's a subtle shift, but it changes the shape of the table and the way we think about the transition from one block to another. What I love about all of this is that it reveals the periodic table as something alive, something still being refined. It's not a finished monument. It's a working document. And the refinements aren't just about tidiness. They reflect deepening understanding of how electrons actually behave in atoms, which in turn determines how those atoms interact with the world. And speaking of how atoms interact with the world, let's talk about something that connects all of this abstract quantum mechanics to your actual life. Because the periodic table isn't just a chart on a wall, it's a tool. It's arguably the most powerful organizational tool in all of science, and the way it's structured lets chemists and materials scientists predict behavior, design new materials, and solve problems that affect billions of people. Consider the semiconductor industry, the entire digital revolution. Every computer chip, every smartphone, every solar panel depends on our understanding of where silicon and germanium sit in the periodic table and how their electron configurations give them their peculiar electrical properties. Silicon is in Group 14, right in the middle of the P block. It has 4 valence electrons, which means it can form 4 covalent bonds, creating a crystal lattice that's neither a good conductor nor a good insulator. It's a semiconductor. And the magic of semiconductors is that you can tune their electrical behavior by doping them, which means deliberately introducing tiny amounts of neighboring elements. Add a trace of phosphorus from Group 15 with 5 valence electrons, and you get an extra electron floating around. That's an N-type semiconductor. Add a trace of boron from Group 13 with 3 valence electrons, and you create a hole, an absence of an electron that behaves almost like a positive charge carrier. That's P-type. The entire logic of doping comes directly from the periodic table's group structure. You look at silicon's neighbors, you count their valence electrons, and you know exactly what they'll do when you introduce them into the lattice. That's the table working as a predictive tool, just as Mendeleev intended, except now the predictions are building the infrastructure of modern civilization. Or think about lithium-ion batteries, the ones in your phone, your laptop, probably the device you're listening to right now. The choice of lithium as the charge carrier isn't accidental. Lithium is the lightest metal, the least dense solid element, sitting right there at the top of Group 1. Its small atomic size means lithium ions can slip easily between the layers of a cathode material. Its position in the table tells you it readily gives up its single valence electron, making it an excellent charge carrier. And the cathode materials themselves, cobalt oxide, iron phosphate, nickel manganese cobalt oxide, are all transition metals chosen for their ability to accept and release lithium ions reversibly, a property rooted in their flexible d-electron configurations. Every component of that battery is a conversation with the periodic table. And this brings us to something that Mendeleev himself might have found deeply satisfying, because it closes a circle that began with his original insight. He believed the table wasn't just a catalog, it was a law of nature, a reflection of deep order. He believed it could predict the unknown. And here we are, more than 150 years later, still using it to predict, to design, to discover. The elements beyond 118, if we ever make them and study their chemistry, will either confirm or challenge our quantum mechanical models. The relativistic effects we talked about earlier, the ones that make gold golden and mercury liquid, become even more dramatic as you climb to higher atomic numbers. Some theorists predict that element 120, if synthesized, might not behave like a classic alkaline earth metal at all. Its electrons would be moving so fast, warped so heavily by relativity, that its chemistry could be something genuinely alien to us. Not just a heavier version of barium or radium, but something qualitatively different. An element whose outer electrons occupy orbitals so distorted by relativistic contraction and expansion that the neat column-based predictions we've relied on for a century and a half might simply stop working. And that's a remarkable thing to sit with for a moment. Because the periodic table has been so reliable, so astonishingly good at organizing our understanding of matter that we almost take it for granted. You look at a column, you see the trend, you make the prediction, and nature says yes, over and over again, for 150 years. But there may be a frontier, somewhere out past element 118, maybe around 120, maybe further, where the table starts to blur, where the organizing principle that Mendeleev glimpsed in 1869, that Moseley anchored to atomic number in 1913, that Bohr and Schrödinger explained with quantum mechanics in the 1920s, where all of that begins to fray at the edges. Not because it was wrong, but because it was always an approximation, a breathtakingly good one, but an approximation nonetheless. Let me explain what I mean by that, because it's a beautiful idea, and it's worth understanding clearly. The periodic table works because electron shells fill in a predictable order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on. That off-bow sequence we talked about. And the reason the table has the shape it does, 2 columns here, 6 there, 10 in the transition metals, 14 in the lanthanides and actinides, is because those numbers correspond to how many electrons each type of orbital can hold. 2 in an s orbital, 6 across the 3p orbitals, 10 across the 5d orbitals, 14 across the 7f orbitals. The table is a map of quantum mechanics made visible. But here's the thing. That off-bow sequence, the order in which orbitals fill, is itself an approximation. It works because, for most elements, the energy differences between orbitals are large enough and predictable enough that you can say with confidence, this orbital fills before that one. But as you go to heavier and heavier elements, those energy gaps shrink. The orbitals start to crowd together. And when you add in relativistic effects, the fact that inner electrons in superheavy atoms are moving at appreciable fractions of the speed of light, which changes their effective mass and the shape of their orbitals. The simple filling order can break down. Orbitals that should be distinct start to overlap in energy. An electron that should go into one subshell might instead go into another because relativity has reshuffled the energy landscape. We've already seen hints of this. Remember oganesson, element 118? It sits in the noble gas column right below radon. You'd expect it to be a gas with a full outer electron shell, chemically inert. But theoretical calculations suggest oganesson might actually be a solid at room temperature, if you could make enough of it to find out. Its electron cloud may be so smeared out by relativistic effects that it doesn't have the sharp, closed shell structure of a typical noble gas. Some physicists describe it as having an almost uniform electron gas surrounding the nucleus, rather than distinct shells. If that's true, it means the very concept of noble gas behavior, the thing that defines that entire column, might not apply to oganesson in any meaningful way. And element 119, the one that labs around the world are trying to synthesize right now, would presumably start a brand new row 8. It would be the next alkali metal, below francium. One valence electron in an s orbital, eager to lose it, highly reactive. That's what the table predicts. But will it actually behave that way? Some calculations suggest yes, more or less. Others suggest the relativistic stabilization of its outermost s electron might make it less reactive than expected, more reluctant to give up that electron than its lighter cousins. It might be an alkali metal that doesn't quite act like one. And element 120 would be the next alkaline earth, below radium. 2 s electrons. But again, the theoretical picture is murky. Some models suggest that the 8s orbital in element 120 would be so relativistically contracted that it pulls those electrons in close to the nucleus, making them harder to remove. The element might have a higher ionization energy than you'd expect for an alkaline earth metal. Its chemistry might look more like something from a different part of the table entirely. Now, you might be thinking, does it really matter? These are elements that exist for fractions of a second, made a few atoms at a time in billion-dollar laboratories. Nobody's building bridges out of element 120. Nobody's putting it in batteries. And that's true. But here's why it matters, and it's the same reason Mendeleev's predictions mattered back in 1869. It's about whether our model of reality is correct. The periodic table isn't just a chart on a wall. It's a theory. It's a claim about how the universe organizes matter. And like any theory, it needs to be tested at its limits. If the table's predictions hold for superheavy elements, that's a spectacular confirmation that quantum mechanics and relativity together give us a complete picture of atomic structure. And if the predictions fail, if element 120 turns out to be nothing like an alkaline earth metal, that's not a disaster. That's a discovery. That's nature telling us there's something deeper going on, something our current models don't fully capture. And honestly, that would be thrilling. Because physics doesn't advance when everything works as expected. It advances when something surprising happens and forces us to think harder. But let's step back from the frontier for a moment. Let's come back to the table as it exists today. The one you've seen on classroom walls and textbook covers, the one with 118 confirmed elements arranged in 7 complete rows. Because one of the things I find most moving about the periodic table, and I know that's a strange word to use about a chart, but I think it fits, is how many human stories are woven into it. Every element on that table was discovered by someone. Some of those discoveries were triumphant. Some were tragic. Some were the work of lone geniuses. Some were the result of massive collaborative efforts spanning decades and continents. Think about the range of human experience encoded in those little boxes. You've got Hennig Brand, a 17th century alchemist boiling down buckets of urine in his Hamburg basement, accidentally discovering phosphorus while searching for the philosopher's stone. You've got Marie Curie, working in a leaky shed in Paris, processing tons of pitchblende by hand to isolate radium, slowly poisoning herself with radiation she didn't yet understand. You've got Glenn Seaborg, a farm kid from Michigan who ended up rearranging the periodic table itself and having an element named after him while he was still alive. You've got Lise Meitner, one of the most brilliant physicists of the 20th century, fleeing Nazi Germany with almost nothing, working out the theory of nuclear fission on a snowy walk in Sweden, and then watching Otto Hahn receive the Nobel Prize alone. You've got Henry Moseley, just 27 years old, whose work on X-ray spectra gave the table its definitive organizing principle, atomic number instead of atomic weight, and who died on a beach at Gallipoli before he could receive the recognition he deserved. You've got Dmitri Mendeleev himself, a man from Siberia, the youngest of somewhere around 14 children, who nearly didn't make it to university at all, and who went on to create one of the most powerful organizing frameworks in the history of science, not through a single flash of insight, but through years of careful, obsessive work, writing out element cards, rearranging them, testing patterns, trusting the patterns even when the data seemed to contradict them. And you've got Yuri Oganessian, still alive as of this recording, the man whose decades of work on superheavy element synthesis completed the 7th row of the table. An Armenian-born physicist who spent his career in a Russian laboratory pushing the boundaries of nuclear physics one atom at a time. Element 118 bears his name. Oganesson. He's one of only 2 people in history to have an element named after them while they were still living. Seaborg was the other. Each of those names represents not just a discovery, but a life, a set of choices, sacrifices, obsessions. The periodic table is the work of hundreds of people across centuries, and it carries their fingerprints even though we rarely stop to notice. And the table carries something else too, something quieter but just as important. It carries the idea that nature is comprehensible, that the staggering diversity of the material world, everything from the helium in a birthday balloon to the uranium in a reactor core, from the carbon in your bones to the silicon in your phone, all of it follows rules, patterns, regularities that a human mind can perceive and a human chart can capture. That's not a given. There's no law that says the universe has to be organized in a way that fits on a poster, but it is. The elements do fall into families. Their properties do repeat periodically, and the reason they repeat is because of the quantum mechanical structure of the atom. Something so small that no human will ever see it directly, and yet so fundamental that it determines whether a substance is a gas or a metal, whether it conducts electricity or insulates against it, whether it sustains life or destroys it. Mendeleev couldn't have known any of that. He didn't know about electrons or protons or quantum numbers. He just saw the pattern. He trusted it. And he was right. So as you lie there, maybe drifting a little, maybe still following along, think about what an extraordinary thing that is. A chart, a simple grid of rows and columns, and yet it contains, in compressed form, the story of how humans came to understand what everything is made of. It connects ancient Greek philosophy to medieval alchemy, to 18th century chemistry, to 19th century pattern recognition, to 20th century quantum mechanics, to 21st century superheavy element synthesis. It's one continuous thread of curiosity, stretching back thousands of years, carried forward by people who simply wanted to know what the world was made of and why. And the thread isn't finished. Somewhere right now, a team of physicists is planning the next attempt to create element 119. Somewhere, a theorist is running calculations on what element 126 might look like, whether it might sit on that fabled island of stability, whether it might last long enough to study its chemistry. Somewhere, a materials scientist is scanning the periodic table for the right combination of elements to build a better solar cell, a lighter alloy, a more efficient catalyst. The table is still working, still predicting, still guiding, and it will keep doing that, long after tonight, long after you've drifted off to sleep. The elements will still be there in the morning. The hydrogen in your glass of water, the oxygen in the air you're breathing right now, the calcium in your bones, the iron in your blood, the tiny traces of cobalt and copper and zinc that keep your body running. You are, quite literally, made of the periodic table. Every atom in your body was forged in a star or a supernova or a neutron star merger, billions of years ago, and it found its way here to you tonight. And every one of those atoms has a place on the table, a number, a row, a column, a story. So let that thought settle over you like a blanket. You're made of star stuff, arranged according to rules that a Siberian chemist first glimpsed in 1869, rules that turned out to be written into the quantum fabric of reality itself. And you don't need to hold on to any of that right now. You can let it go. Let the elements rest. Let the table sit quietly in the back of your mind, with all its rows and columns, all its stories and discoveries, all its people and their lives. It'll still be there when you wake up. It's been there for 150 years. It's not going anywhere. So just breathe and rest and sleep.